Okay, so today we're going to talk about whoa, sorry, it's showing up here, but it's not there. Yeah, we're going to talk about number representations, which is kind of a almost a random topic in the sense that it's a discrete, different topic from what we've talked to before. So it's like a self-contained presentation, but it's a good time to talk about it because for the projects you have a choice of what data types to use for different columns, and this will help to clarify like what really is the difference between integer and floating point and text, and when should I use each. Okay. Whoa, that's hold on, let me check. I feel like I may have an old copy of the slides here. No, I don't. Okay, just kidding. This announcement slides was from last year, but okay, that's wrong too. Shoot. Anyway, so last time we talked about web scraping and something else. What was it? Messy data. Yeah, yeah. Okay, so that's what we did last time. That's the recap. Sorry, I forgot to put in the slide for that. All right, so so this time we're going to talk about like the low-level representation of data, and this is useful for this is fundamental stuff that applies to a lot of data analysis stuff that you'll do. So we know that computers store information in binary, ones and zeros. Okay, these are called bits, which means binary digits. Why do computers use binary? Well, it's simple, it's noise robust. So the difference between a 0 and a 1, between two different discrete values in an electrical system can be quite large. You don't have to, it's less likely you'll make a mistake confusing a 0 for a 1 if you only have two different things you can store. And it's also a convention. Okay, so but somehow we have to use those zeros and ones to represent all kinds of things. So data is not just zeros and ones, but zeros and ones plus some kind of interpretation or context. So basically some kind of rule for determining how to interpret that data. I mean, the zeros and ones. So the encoding defines what the zeros and ones represent. And we saw this with the ASCII text encodings to determine how to translate from zeros and ones to text. But now we're going to be talking about how to do the same thing with numbers. So this particular sequence of zeros and ones shown here can represent two different numbers, at least. For example, it can store 1,147,000, or 1,147,000,000, and so on, as an integer, because if you convert this to an integer, that's what you get. We'll see how in a second. It also just happens to be the representation for the floating point number 901.8184. And just looking at the zeros and ones, of course, you wouldn't know which of those two it was supposed to be unless someone told you, hey, this is an integer, this is a float, or somehow you knew what it was supposed to represent, and you tried both of them, and you decided which one of them seemed to be what you expected, right? This sequence of zeros and ones can also represent the four letters capital D, A, T, A, using the ASCII character encoding, also UTF-8 since it's compatible with ASCII. It also might represent this blue color at 36% transparency if this was an RGBA color, like pixel color encoding. So in other words, if this was part of an image file, this might represent a pixel of this blue color. It could also be 32 different true or false values for each one of these locations, right? So the point is this could be at least 5 different things depending on how we interpret it, right? And of course, any crazy encoding is possible, so you could interpret this in almost an infinite number of ways, but there's some standards that let us deal with this in practice. Yes?
So how many times is UTF actually used? Because I haven't heard of it before.
You've never heard of UTF-8? You've heard of ASCII.
Yeah.
UTF-8 is actually used like everywhere. It's more common than ASCII, actually, in real new systems. People use the term ASCII more commonly because it's been around longer, but any new system that uses text is using UTF-8 because it's first of all, it's compatible with ASCII, but it also stores like emoji and international characters and all that stuff. It's better than ASCII, and it's the thing you should learn. And like if you have a choice for how to store a file, you should almost always choose UTF-8. Yeah. Yeah, so that's one thing you learn in the class. Okay. So you can also store numbers as text. like decimal numbers as text. This is something that is like a source of constant confusion for people, even after doing lots of like scientists I know who are still who worked for years on numerical calculations, still get confused about whether the data they're looking at is like, is it binary in quotes? Is it text? Like, what is it? So like, for example, CSV files are text encoding, right? So your CSV file might have decimal numbers. So for example, the number 12 might be in a CSV file. And in order to store the number 12 in a CSV file, you have a 1 character and a 2 character. And in UTF-8 or ASCII, that would be this bit sequence. And that would be a decimal number stored in ASCII or UTF-8 in a text file, which is different than a numeric representation that we're going to talk about today. So it's not a raw numeric representation, it's a text representation. Similarly, you could store a floating point number like 12.2 e minus 4. That means 12.2 times 10 to the minus 4th. This also is a text string that can be in a file, like in a text file. It could be CSV again, it could be JSON, whatever. And it's just a sequence of 7 different characters. Okay, makes sense? And you could store that with 7 different bytes, and the bits would look like this. Okay, but these things at both are quite different than what we're going to spend the most of lecture talking about, which are the raw integer and floating point representations. Because these are actually decimal numbers. These aren't binary numbers. Of course, they have to be represented in binary eventually, but the way they're represented in binary is actually as text in UTF-8. Okay, so it's a few different steps. I mean, once you get the hang of it, it's not terribly complicated, but like I say, this is an important takeaway from the class. The difference between decimal numbers and text, raw integers, and raw floating point values. Okay, so the downside of using this textual approach is it's kind of inefficient. The reason it's inefficient is because you're using only a small subset of the characters. So you're only using the decimal numbers, maybe punctuation like period, using e, minus. These are only a few of the many symbols available, and so the encoding is kind of like sparse. But the advantage of this is that it's easy to read for both a person and a machine. It's easier in some ways for a person to read than a machine. It's encoded in decimal. People understand decimal numbers. They don't really understand binary numbers so well. And you can overcome some of the inefficiencies by using a general purpose compression tool like zipping it up with gzip or whatever. But this is different than the raw formats used by like MATLAB or any other programming language to do calculations. They don't use decimal numbers. They use raw binary numbers. Okay. So if we're encoding decimal numbers in text, we're only using a subset of the characters, a small subset. So the highlighted orange ones here, those are the characters we'll use. All these other possibilities are not used. So it's a wasteful encoding. We're using 8 bits to represent like something like 16 different values, something like that, instead of 127 different values in total. Okay. So let's move on to real computer native representations of numbers. The first one, the simplest one, is an integer representation. This is for storing whole numbers, okay? So you know what integers are. You can't have fractions, you have whole numbers. These are represented directly in the base 2 positional notation in the computer. So in other words, you take your decimal number, you convert it to binary, and then you store those bits in the computer, zeros and ones. And maybe you leave some zeros free at the top. If your slot is 32 bits long, and you store the number like on one side, and then in its more significant bits, those might be all zeros. Okay. So we use base 10 as people because we have 10 fingers. I guess. I mean, that's probably the reason. I mean, and earlier civilizations didn't use base 10; they used other bases, but base 10 tended to be what was eventually is what we use now. So I would argue that if we were octopuses, we would use base 8 for our numbers. So we go like 0, 1, 2, 3, 4, 5, 6, 7, and then we go 1, 0 after 7. We wouldn't go to 8, right? Because the most convenient way for an octopus to count is using the 8 tentacles they have, right? Okay. So on the top, you see the very basic. You see the number in decimal 137, and the positional notation for numbers actually was an important innovation in math, where you use the different positions to represent different powers of a base. So of course this is the hundreds place, the tens place, the ones place, and you multiply the number you see there times the position to get the total numbers. It's 100 plus 30 plus 7. Okay, that's obvious. The reason why I'm showing that is because once we move to an unfamiliar base like base 2, you suddenly have to relearn these very basic things that are like intuitive and you don't even think about, right? So 137 is 1 times 100, 3 times 10, 7 times 1, all added together. And similarly, the same number in binary is this sequence 1, 0, 0, 0, 1, 0, 0, 1. And you would say it as, it's still 137, or 137, sorry. This number is 137, but it's encoded with these sequences of ones and zeros because it just so happens that the way that you can add up powers of 2 to get that number involves 1 and 8 and 128. Okay, so you would take one, if you were trying to figure out what the encoding was manually, you take the number and subtract the biggest power of 2 you know that can fit into it. So in this case, 128 is the biggest power of 2. Subtract that out, and that leaves a remainder of 9. And then what's the biggest power of 2 that fits into 9? It's 8. That gives you a 1 in the 8's place. Then what's left is 1. That gives you a 1 in the 1's place. Okay. All right, so just like in decimal, we have some very simple numbers like 1, 10, 100, 100, 1,000, 10,000. In the same, the numbers that have only one position set in binary correspond to some important binary numbers like 1, 2, 4, 8, 16, 32, 64, 128. So when you convert those numbers to binary, they look very nice and clean, even though in decimal they look kind of random almost, right? Fine. So you can also take those numbers and subtract 1 from them to get the numbers that have all ones. Like 4 minus 1 is 3, and those are all ones. 8 minus 1 is 7, that's all ones, and so on. Okay. Yeah. All right, so a little joke. There are only, 2 types of people, those who understand binary and those who don't. All right, so I think we're going to skip the practice. Maybe not. I'll do just a quick practice exercise. I want you to write down the binary encoding for the number 21. And then after that, the number 41. And to help you with that, I will show you the powers of 2 here on the left-hand side. So 21 and 41. You might need paper. You might be able to do it in your head. This one, maybe you can do it in your head. The other one, you might need paper. So how do you break 21 into powers of 2? Shout it out. What's the biggest one? Biggest power of 2 that fits into 21 is 16, which is 2 to the 4. And then that leaves 5. And then 5 is what? 1 plus 4, right? So we have 16 plus 4 plus 1. So that's 2 to the 4 plus 2 to the 2 plus 2 to the 0, which means that the number ends up having a 1 in the 0's place, a 0 in the 1's place, a 1 in the 2's place, a 0 in the 3's place, and a 1 in the 4's place. So this 21 is encoded by 10101. Great. 41 is 32 plus 9, so that's basically you combine this 32 value with the 8 value and the 1 value, and you add those all together to get 101001. Okay. But you also have, you can just Google binary to decimal conversion and punch it in, and it'll give you the answer. But you should at least understand how that works. Okay. There are a few tricks. I mean, if you want to impress your friends at parties with binary, then I would tell you the most important thing is to remember that 2 to the 10th power is 1,024. And this is actually the reason why on computers, a kilobyte is not 1,000 bytes, it's 1,024 bytes. And a megabyte is not 1,000,000 bytes, it's 1,024 times 1,024 bytes. Because in the early days, it was easier for them to compute sizes by taking the total size and just like bit shifting it. And so if you kind of ignore the bottom 10 bits, that's the same as dividing by 1,024, which is almost the same as dividing by 1,000, but it's a little bit faster and easier to compute. So yeah, so if you remember that 2 to the 10 is 1,024, which is very close to 1,000, then you can take a big decimal number and figure out how many bits you need to represent it. So for example, the number, and then if you also combine that with knowledge of the first 8 powers of 2, if you just memorize that, 2 to the 4 is 16, 2 to the 5 is 32, 2 to the 6 is 64, 2 to the 7 is 128, and 2 to the 8 is 256. And if all else fails, you just remember that 2 to the 8 is 256 and then work backwards from that. Then you can basically very easily say how many bits you need to represent any number. Like if you want to represent the number 16 trillion, that's 16 with 12 zeros, right? Each of those triplets of zeros is 1,000, so you need 10 bits to represent it, because 2 to the 10 is about 1024. So you need 30 bits for this trillion part, or that's billion. Sorry, trillion has four of those triplets of zeros. So you need 40 bits for all the zeros, and then for the 16 you need 4 bits. So it's 4 plus 40 is 44. So you need 44 bits roughly to represent 16 trillion. Yeah. And the reason that's important is because when you're working with integers, generally those integers have a maximum size, maybe 32 bits or maybe 64 bits, and you have to know, you might have to choose between a 32-bit number, 32-bit integer, so 32-bit integers allow up to 4 billion different values, whereas a 64-bit number is much bigger than that. It's 4 billion times 4 billion. Okay. Okay. Just for fun, you can do addition in binary the same way that you do long addition. You learn to do long addition in elementary school for decimal, where you just arrange things on top of each other and then carry things over when they overflow. So 4 plus 7 is 11. The way we do that is, well, there's technically a carry here between the ones place and tens place. Similarly, if we convert those to binary, you can do the addition, and you end up with, in this third place, there's a carry between the 1 and plus 1 is 2, and 2 is 1, 0, so that 1 carries, and you end up with 1, 0, 1, 1 there. And the same thing applies to bigger numbers, of course. So just like with these bigger binary decimal numbers, you might have multiple carries. The same thing applies to binary. So these two binary numbers here, the 1 and 0, 1 plus 0 is 1, 1 plus 1 is 2. At that point, you need to carry the 2. And then 1 plus 1 is 2. Again, carry the 2 here. 1 plus 1 is 2. Carry the 2. 1 plus 1 plus 1 is 3. So you end up with a 1 here plus the 2 that you carry. And then 1 plus 1 is 2. You carry that. End up with another 1. Okay? I don't know why this amuses me, but somehow it's like it seems strange. Anyway, subtraction also works the same way that decimal subtraction works. Okay, I like to call subtraction addition's tricky pal. And just like you borrow from decimal numbers to do subtraction, you can borrow from binary numbers, borrow from the higher place. So if you're subtracting 161 from 98 from 161, the 8 can't be subtracted from the 1, so you have to borrow a 1 from the 6. 6 becomes 5, and you have 11 minus 8 or whatever. Okay, whatever. Same thing applies in binary. If you have 0 and you want to subtract 1 from it, you have to borrow a 1 from the higher place, and then that that in this case, there's a chain of baras that eventually goes up there. Anyway, but that's not super important, I guess. It's just kind of fun. So coming back to what you probably care about, to figure out whether integers can be useful, you need to know more about what they can represent. So integers can be used to represent negative numbers as well, actually. These are called signed integers that are both positive or negative. But we somehow need an extra bit to represent the sign of the number, right? If all we have are zeros and ones, then like naturally those are positive numbers. We could add another bit to represent whether it's positive or negative. In practice, we don't just use a simple sign bit. We use a different convention called 2's complement because it's easier for computers to deal with. So basically, with 2's complement, you represent negative numbers by rolling over backwards from the top of the binary range. So I have a illustration that works. It works kind of like an old style card odometer. So with these, with a mechanical odometer like this, once you get up to the maximum value, you actually go back to 0, right? So this old cars used to be much less reliable, so they only had odometers that went up to like 100,000 miles. It's kind of funny. But once you got to 100,000 miles, it would go back to 0. So similarly, if you think about the odometer going backwards, if you're at 0 miles, excuse me, and you want to go to -1 miles, you would roll back and end up at 99,999. So when you roll back, you end up at the highest value that was possible. So you treat the range of integers like a cycle, and when you want negative numbers, you go back to the top. So if we're representing 3-bit numbers, signed numbers in 2's complement, which is, like I said, the way that integers work on computers for negative numbers, if you want to store -1, you actually do kind of a rollover. So you take the whole range, you go from 0, 0, 0, which is a 0 representation, to the highest possible value. Normally this would have been 7, this 1, 1, 1. But because we kind of gave up half the range because we want to represent negative numbers, so instead of being able to represent 4, 5, 6, and 7, instead we can represent -1, -2, -3, and -4 in 2's complement by rolling over. So this 3 is adjacent to the -4, right? And the advantage of this weird scheme is that now you can do subtraction the same way you do addition. So the circuitry for doing, and also the manual rules for doing addition and subtraction are the same. So for example, if you want to add -2 and 1, which is like subtracting 2 from 1, you can take this binary representation and do an addition, and you get the right answer. So you can add negative numbers and positive numbers using the normal positive number rules and get the right answer, because they are because the rollover between, like when you take 1, 1, 1 and you add 1 to it, you get a carry out, but if you ignore that carry out bit, it ends up as 0, 0, 0. Yeah. And yeah, so subtraction works like addition. You just need to negate the second number and add it. So we need to learn how to negate numbers. Negation works by flipping all the bits and then adding 1. It just happens to work. So if you want to get -3, you start off with the bits for 3, which are 0, 1, 1. And if you flip all the bits, you end up with 1, 0, 0. And you add 1, you end up with 1, 0, 1. And that happens to be -1. So this is like a little trick that early computer hardware designers figured out for making subtraction, making integer arithmetic easier to support both subtraction and addition of positive and negative numbers with the same mechanics. In other words, the same hardware, the same circuitry. And the reason why you should know about it is because you might sometimes end up with values that are unexpected, and this would explain why. Like if you have overflow of, if you add 2 positive numbers together, you might end up with a big negative number if those 2 positive numbers are too big, because it overflows around to the back end. Although normally normally you'd be able to detect that. I guess a more likely, yeah, sorry. Let me rephrase that. The most important thing actually that this tells you in dealing with data in the real world is that if you happen to interpret a bit sequence as a signed number if you had signed numbers like -1 that was stored in a bit field, it would be like 1 1 1 1 1 1 1 1. If you didn't know that it was a signed number, instead you treated it as an unsigned number, you would end up with this really large number. So suddenly in your data analysis, where there should have been a -1, you now have like 4 billion. And that obviously would throw things off, and that'd be very confusing. Except now you know why that kind of an error can turn up, right? Because in a lot of programming languages, especially like C or C++ or well, a lot of other ones, you can use both signed and unsigned integers. And if you happen to have data that was assigned numbers, and you had negative numbers, and those were stored somewhere, then later on you incorrectly interpret them as unsigned numbers, you would end up with all those negative numbers would be turned into really large positive numbers. Unless they were really, if they were really far negative, then they would end up with like medium-sized positive numbers. But anyway, the most confusing thing is seeing like a -1 or a -2 that ends up being a really huge positive number. Yeah. So integers are a natural representation for numbers, but the problems occur if you run out of space in your representation. That's called overflow. Overflow is when numbers don't fit into the number of bits that you have available. So if we're using 3-bit signed integers, and like obviously 3 bits it's a made-up example to make this easy to see on the screen. In reality, you'll be probably using 32 bits or 64 bits. But if you just bear with me and think about 3-bit numbers, 3-bit signed numbers, if you take 2 plus 2, that should equal 4, right? Here's a representation of 2 and 2. You add it together. You end up with a carry. And this result, 1 0 0, this is 4 in unsigned integers, but as a signed integer, this is actually -4, which is obviously the wrong answer. 2 plus 2 is +4, not -4. But in doing this math, the computer will throw an exception if it notices that there's a problem. It can actually detect the problem because we added 2 positive numbers but got a negative number, and that's pretty easy for the computer to detect that it's a problem. But still, so even though we're not using a simple sign bit, it's still true that the leftmost bit indicates whether or not the number is positive or negative. If it's 0, then it's a positive number. If it's 1, it's a negative number. It's just that we can't interpret the remaining bits directly as an unsigned number and to translate it. So this -1 is 1, but then it has it's 1 1 instead of 0 1. Yeah, so let's skip that. Okay, so if you want to learn more about low-level representations of numbers, you can and how they're used. There's a little video here that shows how arithmetic happens on a computer. I think that's cool to check out on YouTube. Then also, if you need a general engineering course, if you're an undergrad, Computer Engineering 203 is Intro to Computer Engineering, and that's a pretty good overview of this stuff. Has anyone taken that? Yeah. Okay, so you already know this stuff. Okay, good. All right, so just a couple more things about integers. When you're doing multiplication, 2's complement allows you to multiply positive and negative numbers together without any special hardware, the same way as positive numbers. Positive division works as expected. And then one interesting thing is that if you want to take a negative number that has a certain number of bits and then fit it into a larger bit size, like if you take a 4-bit -2 representation, here is 110, and want to represent it as a 8-bit number, the way you do that is by sign extending it. So you take the bit that was in the leftmost position and just repeat it. So 1110 becomes 11111110. And But if it was a positive number, you just add zeros up front. And like I said before, computers typically use 32 or 64-bit integers, and which one you choose might depend on how big you expect your numbers to be. And 32 bits is up to 4 billion for positive numbers, or 2 billion if you're doing signed numbers that could be positive or negative. Okay. But okay, so integers are useful for counting things, of course, but they have some shortcomings. Most importantly, that we can't represent fractional quantities. So if we want to measure something, we probably don't want to use an integer. We probably want to use some kind of fractional number. Now, the fact that we're using binary is kind of is not fundamentally different than decimal, because binary numbers also can have decimal places. Of course, the word decimal place has like the number 10 built into it. So technically, they're not decimal. This is not a decimal point if it's a binary number. It's actually called a radix point. But anyway, if you take a number in binary and 0.111111111, that number in binary is actually is a number that's slightly smaller than 1. That's the equivalent of 0.9999999, right? Because it's a 0 point, and then it has the biggest possible number in every possible place as you go down. So this number in base 2, you notice at the end I have 2 in subscript here. That tells you it's a base 2 number to avoid confusion. This is a number just slightly smaller than 1. And similarly, this second one, 0.00001, with a decimal point in front, is slightly larger than 0. And then, interestingly, 0.1 in binary is 1/2. Because it's not 1/10, because the positions here are powers of 2. So the first decimal position is 2 to the minus 1. The second one is 2 to the minus 2, and 2 to the minus 3. So this first decimal position is the halves place. The next one is the quarters place. The next one is the eighths place, and so on. Okay. So given that we can use binary we can represent fractional numbers in binary, but how do computers represent fractional numbers? So one simple solution that you can do is use fixed point, which is it's actually not common, but I'm going to talk about it as a stepping stone. And there's some cases when you might want to use fixed point in the real world. So this is basically where you take an integer and devote some bits to the positive part, the integer part, and some bits to the fractional part. So you basically stick a radix point, which is the decimal point, I guess, in general base. You stick a decimal point somewhere in the position in the bit sequence. And you always, that as a convention in your number encoding. So this is useful if you know exactly how many fractional places you need, because then you know exactly where to stick the decimal point, and that decimal point will always be in the same place. Like for the cost of goods in US dollars, you know that you need 2 decimal places for the number of cents. So a fixed point representation, where basically you're representing the cost of quantities as the number of cents, the number of pennies. That's a good representation. So the cost of a sandwich is 625 cents. If you just simply decide, in this case, I'm using an integer, 625, to represent a fractional quantity, simply by changing the convention of what each integer unit represents. In this case, each unit represents a fraction of 1/100th. This could also be useful for other things that have a limited range, like if you're representing the distance between cities and you want that to be accurate to hundredths of a mile, you could say that Evanston is 1,321 hundredths of a mile from Chicago, and similarly, it's 79,542 hundredths of a mile from Philadelphia. Okay. Because the range is limited and you're measuring things that you know exactly how many decimal points you want to represent, this can work. So if you're thinking if you're using binary, you can apply the same rule, the same scheme. Let's say we have 16 bits. That allows us normally to store integer up to 64,000, but if we want to allow fractional values, our range becomes smaller because we devote some of the bits to the integer part and some of the bits to the fractional part. And if the thing we're trying to measure is, let's say, the chemical elements' atomic weights, so we have basically a range between hydrogen being 1.0 something and uranium being 2.38 something, point something. We don't have any negatives, so we can take our bits and devote 8 of the bits to the integer part and 8 of the bits to the fractional part, and whatever integer is in the left half is the integer part, and then the right half tells us how many 256ths of a unit are left. Or alternatively, you could treat the whole thing as an integer that is that counts the number of 256ths of an atomic weight unit you're representing. Okay. So these two different. So this large value would be represented like this, and the small value would be represented like so. Here. Okay. So that works. It's simple and efficient, but it only works when you have very limited ranges of numbers. So it's essentially not, it's still an integer representation, but you're just treating the integers differently. You're scaling the integers differently. So like for example, if you're multiplying things, integer numbers, you can overflow very easily. Because like two 16-bit values multiplied together lead to a 32-bit value, and two 32-bit values multiplied together could lead to a 64-bit value. So you can only multiply small values, and similarly, division underflows. If you divide small numbers, you could get less than 0 pretty quickly, and then you wouldn't know what it really was. And also notice that the precision of numbers varies dramatically across the range of numbers. So small numbers in this scheme have few significant figures. Like this number here is 0.00000010. It can be encoded, but it's not very precise because there are only two significant figures, two binary significant figures for the for this number, right? All these zeros up front are insignificant. They just represent the scale of the number. Whereas if it had a very large number, it could have up to 16 significant bit figures, right? So the solution to this problem is to use scientific notation, and floating point is the binary convention used in computers for scientific notation. Okay, so scientific notation of numbers is when you have a factor up front times a base to a power. So usually in human calculations, we use decimals. Like 10,340 would be 1.034 times 10 to the fourth, and this fractional number 0.0424 is 4.24 times 10 to the minus third, right? The advantage of scientific notation is that it gives a compact representation for extreme values, and it allows you to make very clear what the number of significant figures is, right? So this really huge number here, which takes a lot of ones and zeros to write, can be represented compactly in scientific notation by just having a big exponent, 10 to the 24, and then the reverse 10 to the minus 24 is very compact. And the same thing is true when you're representing it in a computer. And scientific notation, that same principle can apply to binary numbers as well as decimal numbers. You just use 2 instead of 10 as the base. So this number, this integer 1,00010 is the same as 1.0001 times 2 to the 5th power. And you can represent 2 to the 5th in binary by notating 10 to the power 101, right? Because this 10 is actually 2 in binary, and the 101 is 5. Okay. And the same thing applies to fractional numbers. You just need a negative exponent instead of a positive one. Okay. So we want to represent floating point numbers in binary. If we study this in more detail, you see that these, when you the important things to store for a binary scientific notation number are the fraction and the exponent and the sign. So it turns out that every scientific notation number in binary always has a 1 up front. Because if it was 0 point something, you would have changed the exponent to move it to put a 1 up front. So you can actually ignore that 1. That 1 can be implicit. You need to store the fractional part of the factor up front, the significant figures, and then you need to store the exponent, and you need to store the sign. And so basically what you can do is, if you're using 32-bit, if you have 32 bits available, you want to represent numbers, floating point numbers, scientific notation numbers. With the so-called floating point representation, we take the first bit, we store the sign of the number there. We take the next 8 bits and represent the exponent, so this number that is raised to a power. And then we take the remaining, whatever number of bits here, 23 bits, or 24 bits, I guess. No, 23 bits, it says right there. And store the fractional part. So the significant figures of the number are stored here. And that's basically all there is to it. Except there's some details, like the exponent is not the way that we store positive and negative exponents is to add a bias of 127. So it's not quite the same as 2's complement, but you have to subtract. So this encoding right here in as an integer is actually 124. And when we subtract 127 from it, we get -3, which is the exponent we are actually trying to store for this number. Yeah. Okay. So there's a 32-bit representation that's called single precision floating point, and this is used in basically every computer, standardized in I think the 80s. Before then, every different computer manufacturer had a different standard for floating point numbers, and because you notice that integers are kind of straightforward. You don't need to. So 2's complement was a little bit tricky, but it was pretty convenient, and everyone kind of agreed that was a useful system. Whereas for floating point, there are a lot of choices here. Like, how many bits do you devote to the exponent? How many bits do you devote to the fraction? And then the fact that we decided to ignore the first bit was a choice. Maybe others don't want to do that. And then the way we represent the negative exponents is a choice. And then how we order these, is the sign first, is the exponent first, you know what I mean? All those are kind of arbitrary choices. And because they were arbitrary, there was a time when they weren't standardized, and data written by different computers was incompatible with each other unless you translated it. But anyway, that problem was fixed in the 80s, and now we have a standard representation for floating point, both for 32-bit and also 64-bit. So 64-bit numbers, if we just use twice as many bits, we can devote more bits to the exponent to allow bigger and smaller numbers, and devote more bits to the fraction to allow higher precision. Because remember, each of these red fraction bits is a significant figure in the number. Right? So double precision allows larger, smaller, and more precise numbers. Okay. One interesting thing about that notation is that you actually can't store 0 as a scientific notation number that has a 1 up front. Remember, we assumed that there was always a 1 up front. Well, the one case when you don't have a 1 is when you actually have 0. So there has to be a special encoding for 0 in floating point. And there's also special encodings for positive and negative infinity, which is the result of divide by 0. And there's also a special encoding for not a number, which is 0 divided by 0. And all those have the exponent bits set to all 1s or all 0s, and those are treated differently. And obviously, like, the hardware for dealing with this has to be a lot more complex than the hardware for doing simple integer arithmetic, because it's applying exponents and fractions, and it's doing a lot of stuff, basically, and it has to deal with many different encodings. Okay, so on the floating point numbers have a lot of advantages over integers. They also have some disadvantages, and they're not clearly superior or inferior. And so it's important to understand both integers and floating point, because sometimes you'll want to use an integer and sometimes you'll want to use a float, and there are cases when you'll use both. Okay, So coming back to integers, a 32-bit signed integer can represent all whole numbers between minus 2 billion and positive 2 billion. Okay, that's the range. If you take that same 32 bits and instead encode a floating point number using the standard IEEE notation or convention, then you can represent much larger numbers. So 3.4 times 10 to the 38, that's this huge number with all these zeros. Right? It's a really big number, much bigger than 2 billion. Or really tiny numbers. This is 5.8 times 10 to the minus 39. The number of zeros should be roughly the same, although I think the spacing is different, which makes it look bigger because I'm using a space instead of a comma. But so it seems like that seems good, right? And it seems better, but you'll notice that the number of significant figures is fewer. So if you actually scrutinize this big floating point number, it's 3, 4, 0, 2, 8, 2, 3, and then it's all zeros. So there are only 7 significant figures here, whereas the 2 billion number has 10 significant figures, or 9 point something significant figures. So if you're storing integers in a floating point number, you only have 24 bits of precision. So once you get to 16,777,216, if you try to add 1 to that number, you'll get the same number back. So you don't have integer level precision beyond this size. So because you have fewer significant figures, you can cover a larger range, but with less precision than integers. That's because we have to set aside 8 bits in the 32-bit quantity for the exponent, and that exponent is what allows us to get really big and really small. But that's the cost we pay. All right. So this picture I think is useful for thinking about the difference between integers and floats. And this example uses 4-bit numbers, which is unrealistic, of course, but the idea applies also to 32 bits and 64 bits. So if we have 4 bits, that means we can represent 16 different values, because 2 to the 4 is 16. Integers represent those values. Integers represent, the integer encoding represents the integers between -8 and +7. So 16 different integers gives you these numbers, right? Floating point, instead, it also can represent 16 different values, but the spacing of those values is different, and it's an exponential spacing. So we end up with the possibility of storing some really big numbers on the positive and negative end. So positive, I think 24 and -32, or maybe this should be positive 16. Yeah, positive 16 and -32. I think I messed up the scale a little bit. But anyway, so the reason is you have one fewer positive number than negative number because the 0 takes up one of those slots. But you can think of it basically as positive 32 and -32. And then you can store numbers smaller than 1, fractional numbers. But there's some large integers in the large integer range. Those values can't be stored in floating point numbers because of the exponential spacing. So like -6 over here wouldn't have an exact representation in floating point. You'd have to round to either -8 or -4, something like that. That makes sense. So yeah, integer spacing is constant. The numbers are constantly spaced, or evenly spaced, I should say. But floating point numbers are exponentially spaced, or logarithmically spaced, depending on how you want to think about it. All right, so you have the same number of possibilities, but they're spaced differently. So which one you choose will depend on whether you expect your values to be in this range of high value, be in a limited range where you want high precision, or to be in a much larger range where the precision is less important. Okay. Another thing to be aware of with floating point numbers is the possibility for catastrophic cancellation, which results in a loss of precision. So, for example, if we have these two numbers up here, like -1, 2, 3, 4, so on, these are two numbers that are very close. Let's imagine these are floating point numbers. Sorry, I should have said this only applies to well, I guess it applies to any numbers, but it's important for floating point numbers. If you subtract these two, they're very close in size. They differ only in the least significant figure, right? So the result is going to be 0.000 and so on up to 1. Some really tiny result. In scientific notation, if you did this subtraction, so these are the same numbers in scientific notation, the result here is 1.0 whatever times 10 to the minus 10. So the result has technically shows 10 significant figures, but 9 of those are bogus. Like these actually are probably different because the original values we had were limited in their precision to this 10 to the minus 10 place, right? So by subtracting two numbers that are very close, we ended up with a number that had only one significant figure, which is bad, right? That makes sense? So this example is shown in decimal, but the same idea applies in binary. It's just easier to see in decimal. Okay. So you want to avoid subtracting floating point numbers that are close to each other, which seems like a dumb rule because like how can you avoid doing a subtraction if you want to do a subtraction? But we'll see later on that there's some cases when if you just change the order of the subtraction, you end up doing a subtraction of numbers that are not close together. Or you can change a subtraction into an addition potentially if in some cases. So I want you to think right now about the other operations, addition, multiplication, and division with these floating point numbers, so scientific notation numbers. And do these other operations can they lead to a loss of precision? All right, so think about that, and we'll continue in a couple minutes. So, what do you think? Let's start with addition. I think that one's maybe the easiest one. Let's do a poll. So there are two options, right? Either you can lose precision or you cannot with addition. Okay. So who thinks that you can lose precision with addition? Okay. Who thinks you cannot? Come on! No, actually you can't, which is surprising. You can't lose precision, as far as I know, unless I'm thinking backwards about this. Because if you're adding two numbers, okay, assuming those numbers are both like positive, because otherwise, if you're adding a positive number and a negative number, it's subtraction. Okay, so I hope you at least understood what I meant by that. If you're adding two positive numbers, then it's possible. I mean, it's true that one of them could be bigger than the other, and so you could lose the figures that were in one of the numbers, but the result is still going to have a large number of significant figures, like the number of significant figures that was in the original number. So Let me just write this out. Let me show you how this works. Okay, so all right, so let's say we have, I don't know, 3 times 0.437 times 10 to the 10 plus 7.438 times 10 to the, we'll have different numbers here. Let's start off with 10 to the 10. Okay, so obviously if these are the same scale, we can do the addition and get some answer, which I'm not going to do, which is like 10.8 something times 10 to the 10. So we don't lose precision there. The one problem you might think of is, what if this number is really small? Like, what if this is 10 to the minus 10? So we have one big number and one tiny number. Then, so it's true that these significant figures for the second number will be lost. They'll be unaccounted for, because if we're limited to, like, let's say that we only had, so 4 sig figs are available in the computer, basically. Let's see if that's the case, then this addition with this tiny number plus this big number will result in the original big number. Like this. So we did lose these figures in the second number, but the number of significant figures here is 4. So we still have a number with high precision in the result. Now the number wasn't affected by this other tiny number, but that's what we expect. So we didn't lose precision there. Was there another case? Does that make sense? Does anyone want to argue? Like, does anyone have a counterexample that they think might lose precision?
What about 1.999?
Yeah?
Yeah, like plus 0.0001.
This one? Okay, so here. Oh. So here, the answer should be 2, right? So it's true that these are 0. So these maybe look like they're not significant, but we do still have 4 significant figures. These zeros are significant.
What about both of the two numbers are 10 to the 10?
Doesn't matter. Then the result will be times 10 to the 10.
Yeah, so what's the difference between this example and the example?
The subtraction?
Yeah.
Yeah, so the subtraction example was, let's say we have this number and we subtract this. The result is this, and we only have one significant figure. We don't know what comes afterwards. So this will be converted. This will be converted into 1.00 something times 10 to the 1, 2, 3, 4, 5, 10 to the 5th, something like that. And then, but these here are not significant. We're losing precision, yes, because we started off with two numbers that had 1, 2, 3. We had one that had 6 digits of precision. The other one had 5, let's say, or it might have had 6, and the result only has one significant figure of precision. Yes. Because it's a subtraction of two numbers that are close in size. Whereas for the addition, it was, for all the cases of addition we can come up with, it's not true. And for multiplication and division, yeah, question? Well, I'm assuming that it's up to us to say, but if we say that they're all significant, so a problem arises if we start off with many significant figures and end up with few significant figures. If we only had one significant figure to begin with, then we wouldn't care if we ended up with one significant figure after the calculation, right? Because we wouldn't actually want more. And if we ended up with a number that had more, we'd probably round it to have fewer. But in this problem, I'm assuming that these are all significant. And actually, that's why the example on the slides used like a number where it was clear that they were significant figures because these are all different digits. And when you subtract these two numbers that are very close but different, you end up with this other number that it has just one significant figure. And yeah, so you have a loss of precision there in the subtraction. Well, the result is correct, but only correct within one significant. So we don't know whether the result is 1.000 or 1.253 or 1.003 or something like that. So we end up with a number that looks. The problem is that we would not necessarily have expected to get such an inaccurate answer, starting off with two numbers that had so many significant figures that were very precise. We start off with two very precise numbers, and we end up with an answer that's not very precise. Now, actually, if we just stop there, we might be okay. The problems arise if we take that result and then, for example, multiply it with another number to get back on the scale that we were originally at. So, okay, so it's true that in a calculation, if these are sizes, for example, right, and we're calculating the difference between the size of two things, and it's very small, and we look at it and say, okay, this is very small, I don't care about it. You might, because the fact that it's small might mean that you can ignore it, and that would not cause any problems. But if you then take that number and multiply it by something else, which leads back to something on the same scale as the things you care about, then you might come to the conclusion that yeah, I think I actually need a more drawn out example to really make this clear. Yes?
For the second row,
Yeah.
this is supposed to be minus 1.23 times 10 to the negative 1 instead of minus 0.1.
I believe it's this was done incorrectly. It should have been this should have been similar to this one. It should have been 1.2. The decimal place is in the wrong way. Yeah, sorry about that. Okay. So, yeah. So multiplication and division actually also don't lead to catastrophic cancellation and don't have any problems. And so the next slide, so to answer your question that you just had, the next slide gives a better, it doesn't fully answer the question, but I think we'll give a better answer to why we care about a loss of significant figures. So what about integers? Can we have a loss of precision when dealing with integers? I guess we can. I mean, you can just take the same examples and remove the decimal point, and somehow we started off with many significant figures and we ended up with a small one. But with integers, I mean, integers don't represent measurements, but rather discrete quantities, so we don't really think about significant figures with integers. The problems that arise with integers usually are overflow, where the value gets too large to be represented, so it ends up not having space to fit, so we don't know what the answer is, or it gets so small that it can't be represented, and like if it's less than 1, and we want to represent a fractional quantity, but we can't because it's an integer. Those are the kinds of problems that show up with integers. Right. But to try to make this catastrophic cancellation problem more clear, I have an example here that deals with the quadratic formula. But in general, so the field of numerical methods deals with math on computers, especially floating point numbers, which have limited precision. And this is a subfield of applied math. There used to be a class taught by Jorge Nosadal for the applied math department, ECS 328, which is no longer taught on numerical methods, unfortunately. But I took that here when I was a grad student. And there doesn't seem to be an equivalent class anymore on numerical methods. But anyway, the applied math people here and other universities and in general, some of them focus quite a lot on how to do calculations involving numbers in such a way that you get an answer that's precise, that minimizes errors, and also has good runtime. Like there's a difference between a mathematician coming up with a formula for the answer and actually being able to implement that answer, that formula to get an answer when you're dealing with floating point numbers that have limited precision. Like if you're doing a calculation that runs for like hours and days and it's doing just calculation after calculation, these little errors can add up, and when you're taking small numbers that have little precision and multiplying them back to get big numbers, you suddenly end up with big numbers that you think are significant, that you think that because they're on the same scale as the things that you talk about, but they're actually ended up being the product of small numbers that had few significant figures, and therefore you have you should not have any confidence in your final result, even though theoretically your calculation is based on formulas which are true, which are correct. Every time you implement an operation on a computer, there's some error, there's some round off, and those things can cascade to lead to really bad answers, even though it seems like everything you're doing is correct. But that's why there's this whole field of numerical method to deal with errors in runtime. So an example of this is the quadratic formula, which you learned in high school, right? So to figure out the roots of a quadratic function, you can use this formula, right? This actually doesn't work so well on computers in certain cases because you have a subtraction that can have catastrophic cancellation. So when this b term, this minus b, is roughly on the same scale as the b squared minus 4ac, you can end up with a number that has very little significance, very little precision, I should say. Whereas there are alternative forms of this formula that give the same answer theoretically, but don't have the same catastrophic cancellation, basically because the formula is different or the order of operations is different. So these variations down here for the two values x and x2, the two different roots of the quadratic function, they don't have the possibilities to subtract two numbers that are the same because the subtraction, we use the sign of, we end up not doing subtraction, but the addition of two numbers have the same sign, basically. Which, I don't know how these are derived, I guess, but apparently these also are valid for the roots of the quadratic functions. There's a different catastrophic cancellation that's still possible here when b squared is roughly the same scale as 4ac, but one of the two subtractions here was eliminated, and that helps. Yeah. So something as straightforward as solving a quadratic function, solving the roots of a quadratic function, if implemented in a straightforward way, because of the fact that we have limited precision in the operations and based on the order of operations in this particular formula, we could get really imprecise answers for certain variations of this formula where the A, the B, and the C happen to be such that this equality kind of holds almost, right? Even though theoretically it's the right, it can give you the right answer. The computer will end up rounding at the worst possible times, basically, and then percolate errors up to the final answer. Okay, so we have a couple of different numeric representations, and one of the key takeaways from this, or the things you should learn from this, is when to choose different number representations. So, for example, when you're counting things or labeling things, you should use integers, because it doesn't make sense to have 1.5 as like an identifier for for staff in an organization or something, or if you're counting up the quantity of items in an order, there's no reason why it would ever be fractional. And by using integer instead of floating point in that case, in both those cases, you end up with the possibility of storing larger values with more precision. On the other hand, if you're measuring things, you usually should use floating point because that allows you to represent fractional quantities and to do multiplication and division without worrying about overflowing the limited size of the integer. There's some cases when fixed point representation makes sense. For example, there's some cases when you might not, if you're doing embedded systems programming, like if you're programming a toaster, which I suspect most of you won't be doing, but maybe like Arduino or something like that, you might actually not have floating point available, so you can use fixed point representations for fractional quantities. But there are also cases, interestingly, when rounding is desired. Like if you're dealing with prices and you want to compute the cost of something and give it to a customer, like in a bill, then it might make sense to use fixed point representation, like an integer representation for the price, because you don't want to tell the customer that the candy bar after you apply tax is like $1 at 0.257893. Like that doesn't make sense. They're not going to pay you in fractions of a penny, so you actually want it to round. So using fixed point representation, so counting the price in cents, like pennies, is actually a better choice here than using floating point. And then within each of those things, floating point and integer, you sometimes have a choice of using like 32-bit or 64-bit quantities. Of course, you can always go with the bigger one if you don't know and you don't care about the space. But your calculations will be faster if you use a smaller size, and it's okay to use a smaller size. So if you don't need values greater than 2 billion, you can use 32-bit integers. If you do need values larger than 2 billion, you should use 64-bit. And then for floating point, if you're choosing between single precision and double precision, this is 32-bit, 64-bit. You can think about the number of decimal digits of precision that you want. And single precision gives you 7 decimal digits of precision, whereas double precision gives you 16, a little bit more than twice as many. Also gives you a larger maximum range, 10 to the 38 instead of 10 to the 308, which usually is not important, but unless you're doing like astronomical calculations or something, like how many atoms are in the universe, something like that. Yeah. I think I mentioned before that floating point is difficult for computers to work with. And so to recap, numbers as well as text are represented in binary by computers. And often when we encounter data, it's actually decimal numbers encoded in text. But then when we load that into the computer to do calculations, it generally always is converted to either integer or floating point representation to do the calculations. And in a database, usually you store numbers not as text, but as either an integer or floating point value. Integers represent whole numbers. We use signed integers with 2's complement to represent negative numbers, and they're useful for counting and identifying records. Whereas floating point is a binary scientific notation representation, useful for measuring things, and it can represent tiny fractional values and huge values with equal precision, like the equal number of significant figures. And there's both single and double precision, useful for measurement and calculations. But the one thing to keep in mind is that subtraction with floating points can lead to catastrophic cancellation. That's not a disadvantage of floating point per se, but that's something that you should be aware of when you're using floating point. That especially if you're doing a big simulation with a lot of calculations or a long calculation, it could be that that you end up with bogus results because you're losing significance in some of the earlier steps that gets percolated to the final result. And that's it. I'll see you on Tuesday.